Yep, we over practice test today. Let's see. Well, might as well do that now. All right, depth first search. All right. So starting at a right, two options. First one that we'll go to first. Is going to be B, right? Because we're always going to be using what's in the underlying table that's backing it up. And since it's depth first search, we just keep on going until we run into a dead end. And with this particular graph, it's connected well enough that no dead ends are going to be reached as we go through. All right, so second vertex B, fourth is D, and lastly I. Breadth first search does require us to keep track of things in the queue. There's no submit button for the chaining lamp. I'll have to take a look at that. All right, so A is out first. B and D will get NQ'd. B gets DQ'd. NQ, C, and E. DQD. He's already NQ'd, so we'll NQ that again. So let me start numbering things here. 1, 2, 3. Fourth up. Will be C, which will tell us about F. DQ. Yeah, depth first search uses the runtime stack, generally speaking, and breadth first search uses a queue. Right, so we went on here. E, okay, that was the C, right? Good, we went there already. Okay, lost track of things. All right, F and H. F's already in the queue. And there, we'll go to G. Fix out. H we already know about, so we go to F. That tells us about I. And then H. He told us about that one, doesn't much matter. And then we go to I. All right, second vertex output B, fourth C, and lastly I again. Let's graph contain a Hamiltonian circuit. Right, so we need to be able to hit every single vertex. exactly one time and get back to where we started. And the best we're going to be able to do is make a trail, and that's not a circuit, right? Because once we get through this cut vertex, we're going to have two subgraphs. We would have a subgraph, 3 nodes up here, and a subgraph, 2 nodes here. And that's going to cause us to not have a circuit. Euler is all about the degrees. Everybody's even, so we have our circuit. Minimum spanning tree, prim. All right, so starting at A. So A is in the graph, 3 options. First up is G. 3 options at this point in time. We'll take H. Right, and then eliminating edges to a vertex that's not in the tree. That's not the shortest of those possible edges. Then F. And we're done. So FTH, H. Right, if we were to keep on going, these 2 edges will become available. Right, so an Euler graph is we want to consume all of the edges. So as we're traversing from one vertex to another and going, or just going through a vertex, right, we need an inbound edge and we need an outbound edge for that vertex in order to be able to pass through. Right, so if we only have like a vertex attached to the tree, right, and we have some sort of tree over here, a tree graph, and we have one node hanging off the side, right? There's only one inbound, and there's no way to get back out. Since Euler cares about using all of the edges, not having an even degree is problematic. If this did have an even degree, because there were additional bits of graph to go to, and for every road in, there's a road out. And so when we come back along and say that these graphs are connected type thing, we have a road in and then a road out to take us all along the way. So when every degree has an even, every vertex has an even degree, we get the road in, the road out, and we have a circuit. But if there are 2 nodes that are odd and everyone else is even, then we just have a trail. All right, so continuing along here, we have 5, 3, and 8, right? Prim's one of our greedy algorithms, likes keeping up with short paths. All right, 1, 4, and 6. All of our other edges are consumed or been discarded, so D's running the show here at the moment. C gets added, ditch the 4 edge, replace it with 2 as a possibility, which we'll go ahead and use. And only 1 edge left. And that would be our minimum spanning tree. Yeah, so with prim, we choose closest node not in the graph to be added to the graph that we can connect to. Right, the closest node in the graph later down the line, you can see we got a 1 edge added much later. We had a 3 edge and a 2 edge and a 3 edge added before the 1 edge, but that was only 1 away from the graph once D became in the graph. Otherwise, it was still further away. Right, so the shortest way to the closest vertex to the graph might be a better way to state that. Because we had A to B for 5 for a long time as the only known possible way to get to B, but as we kept bringing additional vertices in the fold, I replaced the 5 here with the 4. We kept on processing, we found an additional edge, and replaced that 4 with a 2. Remember, this is one where we have a table. And that just tracks our various vertices. All right, how do we get there? How far they are? Do we know the shortest path? All that fun stuff. And that table helps keep things organized. Right? We can keep things organized effectively the same way with the drawing, just by saying little dashes on possible places we can go and a full line. Right, so when I had with B and G, right, we could have gotten to B from A, 4, 5, and G from A for 1. And once we actually did go to A, checkbox here, which meant I just completed the line, saying, yes, there is now a path between these two vertices. All right, Kruskal. Kruskal does want to sort everything first. All right, so let's get our, let's do it one by lane. These are 1 edges. We got BC for 2, GH for 2. We got 3 is AF, DF. 4, see just the BD. 5 is an FH, B, FH. E for 6, EF for 8, and FG for 9. So we got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 4, 6, 8, 10, 12. All right. Okay, so we'll just go ahead and start consuming. Add an edge. If we create a cycle, remove it. Add an edge. All right, so what we're looking for here, which edges because the cycle before them are removed, right? So no cycle net removed. BC, no cycle removed. GH, no cycle. AF, no cycle. DF, no cycle. BD, create a cycle. AB, we'll create a cycle. FH, where is H? All right, that's already in the tree, so that creates a cycle. DE, it's not create a cycle, and we have our minimum spanning tree, so we're done there. And FH. Any questions with Kruskal before I wipe away the board? It's a simple graph, so FE and EF are the same thing, and they are equivalent. But we will, everything's alphabetized with graphs. You alphabetize them in the list or in the matrix, or as when labeling them as per vertices, unless it is a directed graph, in which case EF and FE aren't necessarily the same edge. So in that case, order does matter. But that right? Because if we look at the underlying, right, somewhere we're going to have E and F. E and F inside the matrix or the list. When we say E goes to F and F goes to E, being the same edge. Since it's the same edge, no sense in listing it twice. Uh, what shapes? So A goes to B. Where the B is, A goes to D. The A going back and forth. All right, so it's not a directed graph. Not that we're asking for the type, we're asking for the shape. All right, so B goes to C, C goes to B, and C goes to D. All right, so it's a cycle graph. It is also a complete bipartite graph. Right, because we could redraw this as A and C in one set, B and D in the other set. So a complete graph would have everyone connected to everyone. A complete bipartite graph means everyone connects to everyone in the other set. Since a bipartite does not allow connections within the set. No, not all graphs are going to be bipartite. And as soon as I add one of these edges in here, it's not going to be bipartite. Not all graphs can be split into bipartite. Half of cycle graphs are bipartite. Right, if we go to a bigger cycle graph, one, two, three, four. If I stop at 5, it stops being bipartite, but at 6, any even cycle graph is bipartite. Right, because I have 2 not connecting to 4, 6. So we can have 2, 4, 6. But there is only going to be 2 outbounds, so it's going to connect to 1 and 3. Right, but not connect to 5. So it's not a complete bipartite, but it is bipartite. So all cycle graphs with an even number of vertices in it is going to be bipartite. Okay, H. H is our starting point, and C is our target destination. All right, 2 possible paths to build. Shorter is kept. Longer paths not kept. So we got a path here at 6 is not an improvement. You have potential path over there 5. All right, so that one's 8 away. This one's 5 away. And so take the shorter path. All right, so we got an 8 and a 13 here. So 8 away versus 8 away. First 8 away will be taken. Speeds before table. All right, 12 is not better than 8. And we have a possible path there. Second 8 is taken. All right, so we have 5, 8, 9, as opposed to 2, 1, 8, 10. That 2 is thrown away. And shortest path there is 9. Any programming questions on the test? Probably not. The only labs we had was the lists and it's just the matrix. Do we do a adjacency list? I forget. Yeah, graph list. Right, graph matrix and graph list. Right. So if there's coding questions, it'd be there, but so much new code as far as that's concerned, where we've already had link-based code questions and stuff like that, and array-based code questions are nothing worth spending time on at this level. Did I forget to click on somebody? I put a D there, and it's saying it doesn't like D. No, I definitely, that is not D. I should have typed F. Not too sure why I typed D. Next one, A, B, C, F. Misentered the data. All right. Any other questions about the practice test or the test before we roll on? Big O. Sometimes we'll need to know the big O. I wouldn't stress the big O for the graphs test too much. But we saw like all Floyd-Warshalls, all pair shortest paths. That one's V cubed. It's a nice, straightforward algorithm. Thing. Easy to come to O notation. The other algorithms are a little bit heavier duty. Let's go to student view. Let's see what's going on with our submit button while we're here. Seeing a submit button myself here either. Okay. It's submitting nothing. That's a big problem. All right. Try that again. I didn't do that right. All right, one more time. All right. Helps when you click all the buttons. All right. better. About that again later if we need to. No, all against wrong knee. Where am I? Why isn't it? All right, well, not quite sure what's going on with my new button here. Don't have permissions. Well, all right. I'll have to figure the upload out later. Let's see. One moment here, bear with me. All right. Yeah, it was not in the right profile. Okay. If I recall correctly, we talked about action briefly last week. That's the process of, right, so after a collection round, or after time in a reference counting scheme, the free areas. Um, that's always that was whatever. All right, so after rounds of collections and or time with our reference counting, garbage collectors, areas of free space, available free space. And we're done to say that available free space can become fragmented. What ass? What the heck is going on here? Oh, fun. Fun typing the same thing more than once. Going on with my cookies? Could be the internet. I am rocking on a hotspot here. All right, we're going to change technology patterns here. Yeah, all right. Okay, that's not Windows here. All right, I will have to post this after the fact because technology is so much fun. Okay, so third time's a charm. When fragmentation in the heap occurs after objects are reclaimed, we can run into a problem when trying to allocate memory. If the memory is broken up too badly, won't be able to service the request. And so compaction does the job of juggling data and relocating it into a better position. All right, let's see if we can find a table. All right. Hmm. Say we have these various objects taking up space. Taking up space in memory. The end goal is right. We want to collapse everything. Collapse it all so that there is a single continuous block of memory allocated in all the free space. One large block itself. All right, so a simple compaction. Really? Okay, that's kind of fun. It's my default paste. All right. All right, so we just go to our first hole, find the first object after that first hole, and then just move it along. For example, it does my paste over there. Not well at all. Okay. All right, so there are no longer any gaps. all external fragmentation was removed. Now, we're going to come back to this concept again in a minute here. Let's new section. Let's talk about fragmentation. All right, so we have three types of fragmentation. We have external fragmentation. As we saw above, we have internal fragmentation and data fragmentation. So external fragmentation. We have space between allocated blocks of memory, right? And we're using the term memory. RAM, random access memory, which is typically type of memory that we think of when we're talking about a computer's memory, but disk is also memory, right? That's persistent memory as opposed to volatile memory. So same thing can happen to your files, where you download a file, you download 20,000 other files, which probably on average how many files are actually downloaded in a day. Just look at your temporary internet folder and see how many files are floating around in there. Files will also get deleted, right? So basic, we have a brand new disk, and it just tends to fill from the first to the last. But as time goes on, files come and go, programs get installed and uninstalled, programs create files, then ditch those files on a frequent ongoing basis. So we'll create free spaces on your disk. And so disk or RAM, same thing, either place can get it. But it's basically it's created as memory gets yielded back to the system, be it RAM or disk. Internal fragmentation. So this is space within an allocated block that isn't actually used by that block. Let's go. Let's over here, demonstrate plus whatever class whatever, and we say int x, we say y, and then we say float z, and we start spinning out whatever. Right, so this data type is taking up all of 12 bytes for our whatever class. And let's establish a foundation of how big things are. Size of int. Or whatever type, and we have a bool type, which we technically only need a single bit of space. Let's store that, but 1 byte is what it would typically take. You'll notice 4 plus 4 plus 1 and 12 have a little bit of an inconsistency in their equality, in that they're showing as inequality. Most systems have a 32-bit word size, which means that anything that takes a word or more size in memory is going to be required to start its allocation on that edge. So what that means right, see, these are our 4-byte blocks. So we have 4 bytes for this block. Copy paste kind of didn't work. I wanted that too. Bytes. Let's try that one more time. Like that. Paste and paste. All right. Lost my line. Terrible. All right, so our first int takes up this box, and it takes up all 32 bits. And my bool takes up this 1 byte. So we've allocated 1 byte of space for this. 1 byte here, leaving 3 bytes available. So if I had a smaller type here, we'll see it fit there, but it's not. And then our float takes up all 4 of those bytes. And so if we go ahead and do let's say char in here, char 1, and char. And our second type who needs a semicolon, right? New line should be good enough. All right, so char takes 1 byte just like a bool. You can see that this time around, where's my eraser? No. All right, so this Y1, instead of going on over to the next word, it just takes up 1 more byte within the word. Since it's smaller than a word size, it will fit here. So the word in which you define your fields inside your type can have a direct impact on how big it is. If I take this exact same type and weave in my chars and have them interspersed, should say it's going up to 16 now. And so taking more space. The schemas of both of these two types are identical, but the footprints are not. Both have 2 chars and int and a float because of the order in which, yep, semicolon, thank you. Order in which I defined them, things are not working out. Most of the time, most types within inside a class are 4 bytes or 8 bytes in size. So this doesn't necessarily pop up. Definitely doesn't pop up all the time. But it can come into play at points in time. But so this is going to be internal fragmentation, right? This space that is over here, it is completely wasted. right? Nowhere in the code are we going to intentionally try to use those 2 bytes of space, because the char is 8 bits, and that's the full range 0 to 255. That's all the values that we can store in that single char. So yeah, so int takes 4 and float's taking 4. And since the word size is probably 4, when I drop 4 byte blocks in memory, remember, when you define a class or struct, the first field is at the first memory address. In fact, let me show memory addresses. That might. Let's see. Create a variable. That doesn't need to have okay, it just needs to exist. All right, so I is there. I has an address. And there's various fields. Will have their addresses as well. And remember the names. Right here. The names of our variables are simply transformed to memory addresses. And chars. Let's see how many bugs I have before I finish all this fun copy paste. Private, oh, silly. Private, lack of access, needs access. Who needs white space? Okay, white space. Okay. I'm missing some memory addresses in the output here. That's interesting. Why don't we like Y? Doesn't want to tell me what its address is. Okay. That that's interesting. Okay, moving along from that. Right, memory address of the object and the first field are the same, just like an array. Right, Y doesn't want to show itself to me for some reason, but it should say 54. I don't actually have C++ installed on this machine, so I won't be able to run it over there. But right, and then 52. Let me get these in the proper order. That's in that order. Right, the addresses of Y and Y1 should be right between those two. So we should have 4 bytes allocated by this. We look at, right, so memory address 84 will be our bytes. Let's go check. So we're going to have at 84, we have byte 0. At 85, we have byte 1, 86, byte 2, and 87, byte 3. And then our next, then we should have y. 88 will be byte 0, which is y. Since it's a single byte data type, it will just sit there. Then 89. That. And this is for char. For char's type. And 90 byte 2 is nothing. 1 byte 3. Also nothing, so reserve space. And then 92. So I should change this to match. All right, that's A. 8A. 8B. And A. B. And C here. Right, so we have 8C here is Z. So we have byte 0. For our fields. And Z wants all 4 bytes. C, D, E, and F. So we have 12 bytes allocated to the structure. It's not going to use these because these 4 byte types, anything that's 4 bytes or more, will not straddle across the word boundary. It's back the drawing I had before here, so we have our word boundary. Oh, let's use a string. Right, the word boundary between every 4 bytes. Every 4 bytes is a boundary, and a type will not straddle across them. It's not going to do this. It would be a more compact way of doing things, but that's not the size of the mouth of the CPU, right? The CPU wants to take bytes out of things, and it's happy to take smaller ranges when pumping this out of memory and into CPU itself, but it doesn't want to do it with the larger ones. I don't recall what all the rationale anymore for why the addressing works that way. But if I recall correctly, that is something you will get into an assembly class. Since you're going to be working more directly with those word boundaries. Right, so internal fragmentation is nearly impossible to get rid of. We have additional internal fragmentation with our Boolean value here, whichever ones are Boolean. Let me go just scroll. And so if we look at our whatever and these bytes, pretty much. Again. Oh, Soon just does not want to play tonight. Or whether I'm feeling to play with it properly. All right, so we have our 12 bytes of space. Right here we had just Y. And Y here is just a bool, which all we really need to represent true or false is a single bit. So we have this wasted space in addition to 7 bits wasted in here as well. And so bit 0, we need bit 2, bit 1's 2 through 7, within byte 0, we don't need. All right, so we're over allocating by a fair chunk. All right, so you want to even more. Let's say we create a bool truth table sort of thing, right? Make 25 booleans. Right. It's probably going to take up too much space. We'll see here in a second. Let's see how well it deals with this. Size of truth table. Size of bool. Indeed, parentheses. Da, da, da. There's one. Lost my parenthesis too. All right, so 25 bytes. 25 bytes for an array of 25 booleans, which we could have handled in a single integer variable, right? And do fun bitwise operations. Right, single int 32 bits, we can handle 32 true false values as long as we were just looking at a particular bit when doing the comparison. You have a lot more efficient space allocation going on with that data type. Arrays are another place, especially strings, where we will have internal fragmentation. So structures, bool, arrays all suffer from this type of fragmentation. And can be quite hard to get this memory back while the objects are in use. Right? Alternative structures can help with it. Once it exists, problem is there. And it's kind of like shopping from Amazon. You order a pair of 9-volt batteries and it comes in a box big enough to hold a tennis shoe. And so there's all kinds of internal fragmentation within the box. It's a bunch of space that is completely unneeded for the job at hand. And that space isn't reclaimed until you get the box and break it down and, you know, basically destroy the box. And at scale, I'm surprised at how much white space or air there's still in a lot of Amazon boxes now that they've expanded to a vertical monopoly and do a lot of the shipping themselves, right? Because the more space you're wasting in a box means the more space you're wasting inside the truck that's shipping the box, which means there are fewer items that that particular truck can convey in a given run. But yeah, sometimes it's still more efficient to do it that way because it's just easier to work with that unit of work than computer working along the same premise. It's too much work getting the perfect size box for every particular thing we might need to ship. So we know we're going to waste some space because it's just 12 different box sizes versus 250 different box sizes. That might be what's needed. Data fragmentation. This is when related pieces of data. When related pieces of data are physically separated in memory. All right, so on disk, you can have this where a single file is split. in disk. But let's say we have, all right, so we create a tree, and a list, one node at a time, going back and forth. I'm trusting for doing this. So your nodes will be called T, and this node's called L. All right, so we create a tree node, create a list node, and then we keep going back and forth. Creating nodes. Click and work. All right, so my related pieces of data are separated in memory. And this separation can cause performance hits. So a particularly intelligent garbage collector that does a compaction could see this type of fragmentation and then compact it to account for that. Okay, answer. Click. All right, so move everything around in memory. As needed, such that I don't know if there actually are any garbage collectors that are that intelligent. So that could be a purely theoretical thing. But if we can arrange things this way, so much the better for being able to process data. We'll talk about locality reference later tonight. The system has a tendency to want to use a large scoop when getting things and then pulling from what's been pulled out of the larger container, caching and all pipelining, all kinds of other various system design is going to be based off locality reference. And if we can get things all nice close together, it's easier to get whatever task is being done. Task at hand done. So I try to smash job done into just one word. Okay, so linked structures are most likely to experience data fragmentation. Files on disk, larger files, or any file larger than what do they call it? Sector size. If we see if I can find a temp folder here somewhere, test. Oh, could be. Let's see. Let's create a text document. All right, some file on disk. Where's space on disk? All right, and the disk system of its smallest just lost my words. smallest unit of work, whatever, that it will deal with. Typically 4096 bytes is the smallest item. Right, so we'll save this file, go back. Right, it says it's 1 kilobyte of space. And there's all of 162 characters in here. Assuming this is Unicode encoding, right? 322 bytes of space. So what's actually needed. So a little rounding going on here. Look at the properties of our file. Right, the actual size, right? So it's not doing Unicode, it's just doing plain ASCII, 161 characters, so we got 161 bytes. And the size on disk, it likes to lie. That or it hasn't actually written it to disk yet, still in the outbound write queue. Not quite sure what Windows is doing there. Let's see if we can start getting getting it. I actually write to disk. I knew open, didn't I? All right, so we're creating fragmentation on the disk here. Much of internal fragmentation because each of these files is taking up a different block. There are some tools that actually tell me where on disk these files truly are, right? Because the file path is not necessarily going to control where things are ending up on disk. In fact, it's not going to have any influence on it at all that I can think of. The file gets created, operating system says, let's go dump this on the disk. And the disk's file system is tracking where our files and where files aren't and where we have space for things. And as these files come and go, right, we start creating some external fragmentation. Assuming they were actually deleted, not moved to the recycle bin, right? You move it to the recycle bin, it's not actually deleted. You're simply just updating the file system to say, hey, we don't want this file to actually be viewable to the user, but we can still recover it magically just by flipping a bit in the file system that says, yes, this file's in use, and here's the file, and all that fun stuff. Where we can get data fragmentation is when we have a very large file. So if you download a large file, one possibility is it'll go to the end of disk where there's space large enough for the entire file, or it might just start filling up space in the disk system as there are spots available. Okay, so that again all depends on how the disk is doing things. But our large file might get broken up. And the way that works is basically the file gets turned into a linked list. At the end of each block of file, there is a pointer at the end of the file or end of that block that points to the next block. Or otherwise, we just need to maintain a separate table that's saying, all right, here's where all the pieces of the file are to get to things. So that just depends on, again, on the disk, and disk management is not a part of our scope. So we don't have to worry about it other than to know that fragmentation, any of these three types of fragmentation happens in any type of memory, be it RAM, hard disk, solid state disk. Data needs to be organized, and we got to get to fit where we can get to fit. And it's just like organizing your closet, right? And you first start from take it all out, put it back in, it's all nice and organized. But over time, things get pulled in, they get pulled out, they don't get necessarily back where they were previously, or the pantry, just depending on what you buy. and consume. You got a box of Cheerios and you got to put it somewhere so you make space. And sometimes you need to do a little partial compaction of the way things are allocated in the pantry so that you can get things to fit in. And all of a sudden you decide to go get a big Costco pie and put that in the fridge, right? Same thing. We have to store those blocks of data, and you have a bunch of different blocks of sized data. Way to arrange it. The best way to arrange it changes based on what the data actually is. All right, let's see if I can't get this to show up. All right, prompt went away. That's good. Let's see if the data is showing up here. There it is. Yeah, it must be jittery internet. All right. All right. Let's see. Let's see. Let's see. So, all right, our training lab. How are things coming along on this one? Someone's already submitted. Since I made the button turn around and show up. All right, take your sort of linked list lab code, use that as the foundation, and we'll start. All right, so let's see. Right, so no, not that. This. Why is there a value? Why isn't the value itself a key? So this question is second. All right, so we have an array of linked lists. All right, so we'll have a linked list class, and we can create an array of them. So we're going to be doing this as a dynamic basis. Right, and whatever these are says they want 25 elements type thing, whatever. Right, so creating an array of linked lists. Then it's just a matter of adding an int as a key and a string as a value. So if we had and key string value. All right, and hash the key, add it, index the value. All right, so you can basically take the hash table lab and linked list lab, dump the linked list lab into your hash table lab, and then we'll change the adding mechanism to make it be a call, right? So we'll have our table. Inside the class, table index that we found, all that, and add key in the value, and just get passed along to your list type, and it would insert into that list, and we would order based off the key. Thank you. Didn't need a semicolon there. All right, so you'd have a list. Array of lists as the table. Well, the key in the string, right? So say we're creating users, data set as users, and we'll use user.id as key and use user as the value. So it's typically when we have objects that we want to store in a hash table. Units and role, whatever things are the object. The name is going to be less unique than the ID because every student within this institution has their own unique ID, but there could be more than one Bob Smith. I know I've definitely run into multiple first names in the class and of course multiple last names in the class. I'm not quite sure if I ever had same first name and last name within the same class, but again, that's just a small subset of the people at school that we have. So there's going to be some overlap. So name is just not as good as the key. If name was our best key value for the data we were storing, then name might have been what we would use as the key value. And the key is what all of the logic will center itself on. The value is simply arbitrary data that is associated with that key. Yeah, so the key is what we'll use. And it helps keep things simple, purposes of the lab, but still somewhat realistic because most of the time when you're using a dictionary to store data, it works like a dictionary works. There's a key and there's the definition of what the particular word means, and hash tables are dictionaries. There's a key value, which is tended to be unique. right? And then all the meanings of that word are laid out as the value associated with that particular key. Yeah, so we would have a class. Right, class node has all that fun stuff in there. We have class list and all that fun stuff in there. Right, where list is our singly linked list class. Right, you should be able to take your, you should be able to go off your graph list one as well. Right, so the code that you put here, this should have been an array of linked lists. It's the same code that we did over here. It's very much same code over here, right? So definitely any code that is your code, feel free to use your code when writing code because it's your code. All right, let's go ahead and take a 5-minute break and then we will continue on. Question: should linked list be sorted by key or name? It'd be sorted by key. Like, so whenever we're doing the lookup, we're looking at see the keys match. So we're looking at by key. All right. Memory allocation. All right, so when allocating new object onto the heap, there are three basic strategies: best fit, worst fit, and first fit. Its first fit is going to making an allocation, find the first available empty or free block of space that is large enough, and use that to fulfill the request. Best fit. Same thing, but we'll find the smallest block that is big enough to complete the memory request. Worst fit. Just going to use largest available block for the request. Block and size. Right, so a free list is a list available blocks of memory. Right, so a data structure is going to be used to keep track of where the holes are in memory so that we can go ahead and find them, right? We're not going to just go ahead and scan the heap every time we want to create an object, try to find a spot that's available. So we're going to maintain a data structure, help us track where things are so that we can complete the request. The data structure that would be used is going to depend on the strategy that we are putting forth for managing that data. All right, so let's say we have various blocks in size available for us. And we have a big one there. And some other items here. So using first fit, allocating 8 bytes in size, go to block 1, right? Our very first block that would fit it. Right, allocating 24 bytes in size, we'll go to block 2. Right, so notes here. So block availability from 12 to 4. Right, our space available block. AZU. That's 24, what, 66. Over there. Right, so the first spot big enough to allocate it. We're allocating 600 bytes. That would go to block 7, and then 8s goes down to 8288. For the lab, if nothing's found, you just return back a null string or an empty string. All right, so basically we're doing a linear search. Linear search, trying to find a block large enough. Using best fit on the same table. My math core, indeed, 56. Fix my math over there. Yeah, same hash function or whatever hash function you want to use. Don't really care what the hash function is for the lab because it's more about the chaining part. All right, so let's allocate 8 bytes. All right, that goes to block 1. That is the smallest block, large enough for the request. We allocate right 12 bytes. Also block 1, and block is removed from the list because it went down to 0. Right. 14 bytes. Goes all the way down to 9. Right. 20 bytes. Right. Finds position 3. The biggest area of space large enough for us to use, but the smallest amongst those options, right? So available options we had 80, we had 24. That's basically we're doing a modified min function, trying to find the smallest that is larger than our number. So we have 20. So we're like, yeah, it's not a valid spot. All right, 80 is our smallest until we find something smaller. 24, right? So forget about 80, 24. Don't care, don't care, don't care, don't care, don't care. This number is smaller, but it's below our floor value. So we ignore it and we end up with 24 as a data point that we're going to use. All right, allocated 30 bytes. Same thing, doesn't work. 80 is our winner so far, doesn't work. 36 is better. Doesn't work, doesn't work, doesn't work, doesn't work, doesn't work. Right, so 36. Block 4 is where our data is going to be dropped in there. Using worst fit. And if we allocate 12, that's going to go to 7. Allocate 80, goes to 7. Allocate 128, it goes to 7. Now, which of these is going to work out best for us? First fit. Right, so right now, if we're maintaining our free list as an unordered set of data, we're talking about a linear search on unordered data. We're not necessarily trying to find like the smallest or largest value in the whole data set. We're just trying to find the first value. So it's not really a linear search, right? Because we have additional criteria for us to exit out. When we had 8 bytes, we found the first spot that was large enough to fit. We stop. Problem is, if we get into a situation where we have a bunch of small values, small free space at the beginning of the list, that we can have problems finding where we want to go in a quick fashion, right? And objects are being created and destroyed all the time, quite frequently. So when you're doing something frequently, we want to make sure that that operation is as optimal as we can come up with for circumstances of the machine as it's spinning around. Right, so sometimes we'll have additional data structures going here or multiple data structures. So instead of just a single free list for all available space, we can have multiple lists. We have a list of areas of memory that are under a kilobyte or 128 bytes, whatever threshold is, and we can have a second list of medium available spaces, which would probably be shorter than the small ones. And then we have a list of free spaces that are large allocations. So we have our under 1K or 1 to 4K and our greater than 4K areas of memory that we can work with. Right, because we can go ahead and do a little bit dividing and conquering. So we do a quick test. How big is the request? And then we can go ahead and eliminate the 2 lists that are not of the appropriate size for a request. Then we can find within those structures. Right? Other things we could do, instead of maintaining an unordered list, we could have a ordered list, right? Because at that point in time, we can do a quick search to find the location to make the request. Quick search. Yes, quick search. A binary, there we go, binary search, which would be much quicker than a linear search, right? Logarithmic time, typically what we're expecting there. Or we might want to have simply just not a simple array structure doing it. Maybe we want a binary search tree to help with the request, right? Because we do the binary search is a little bit of a flaw in how we go left or right. With binary search, if I want a 200 byte allocation and the root's 204 bytes, right? I can go left, but the next value left might be 196 bytes or 112 bytes. And we can have some problems there because we're trying to look for a spot that is bigger than us, but finding it can be a little bit tricky. So first fit is pretty much what they all do to start off with, because when we first launch our application, there's little to nothing allocated on the heap. So the first object that comes along is in the first block, right? Because there's one item in the free list. We have 8 megabytes of free space. Now we have 4 bytes or 40 bytes, however big the object is allocated, and still almost 8 megabytes of free space. And all the objects that keep coming in, they're all using first fit. We just take the first chunk away from that large box and make that large box a slightly smaller, very large box. That's when our external fragmentation crops up, that any of these now need to be considered as alternatives over the others. So as objects get deleted, we will create external fragmentation that way. And then we have to choose from these. Best fit. With best fit, right, when we allocated our 1 byte block here, we had 4 bytes left over. We allocated 14 bytes here. We had 2 bytes left over. And we had 20 bytes going to 3. We had 4 bytes left over. And our 30 went to 36, so we had 6 bytes. So with best fit, since we're going with close enough sized boxes, we can end up with a bunch of small blocks being available. One way to help deal with that is to simply just disregard the small blocks and treat them as though they're part of a larger allocation, effectively tossing some internal fragmentation in there to make the external fragmentation look better than it actually is. And then just when that object gets deallocated, then that full block size becomes available again, right? Or a separate list again later. These are just super tiny things. Like if I'm dynamically allocating a short or an int or a float, then these little spots here are still useful for that, but most objects tend to have a fair amount of size to them, right? Some sort of base for number, it's 4 bytes, 8 bytes, 12 bytes, 128 bytes, whatever it is. But spaces can get a little messy over time. Worst fit. Worst fit is going to be the fastest way to go because keeping track of one very large block of space is not hard to do. You have one very large block of space, and here it is. And then you took a little bit away from it, so I decremented how big the block is, but updated where the beginning of that block is, so we can use that as the memory address for the next request, and we're done. Problem here is if we keep taking away from the big pool of water, we will have problems when it comes along to allocating larger objects because we kept taking away from the largest space. Depending on how external fragmentation grows for our other allocations, could have like 70% fragmentation going on here, but not be able to make the requests successfully operate because things are too spread out in memory. So worst fit would benefit the most from a compaction event because we can just get a big chunk and we can do modified compaction, right? Where we don't actually necessarily need to compact everything, but we just want to go ahead and compact as much as we can around a large free space, possibly the current large free space or other large free space, so that we can get things clean in the spot that we're working on, right? So the strategy basically, clean your room. All right, I'm going to take stuff off the floor and dump it under the bed, sweep it under the bed, or dump it in the closet. Hey, the floor is clean, but we made a couple of other areas a little bit messier to make that space work for us. Right? We can go ahead and use like a min heap. Keep on tracking that, and at any point in time, that the largest block becomes not the largest block. Right? We just readjust that heap. So the heap wouldn't even have to change in space as we're doing allocations. As frees come along, that's where we'll go ahead and update the heap so it can keep track of things. We'll have data structures sitting behind these. We don't particularly care too much for this course which data structures are going to sit behind them, simply how the strategies work for allocating the memory. Well, questions on our memory strategies here? Your space pop. All right. Okay. Okay. Locality of reference. Yes, this is a phenomenon. An autocorrect fix that for me because my brain just definitely doesn't know what to trust. Okay. Of how computer systems work and the strategies that are put into place to optimize for those. All right, so temporal and spatial locality of reference are the two types, and spatial will break down into two levels. So temporal in time locality of reference to a resource that was more recently used has a higher chance of being used again in the near future than a resource that was last used a long time ago. And so we have a program semicolons, whatever, important. Don't correct that. So, level one. All right, so we have this code. Our resources would be X, Y, total, and I. So as the computer is running, this is very simplified example, of course, right? X, Y, total, and I are going to be loaded in memory. All right, so let's talk about computer architecture a little more here. See if I can find one. CPU 2, 3 cache. Yeah, let's just go to images. See if I find a good one. Oh, looks good. Way. All right. All right, so your CPU is going to have the core. The core is where the actual processing happens. And we have different areas of memory on the chip itself. Right, so local memory down here, that would be the RAM. where all of your application code and all the variables, all the stack, all the heap, all that data, global variables, all fun stuff that lives here in RAM, assuming it's not virtualized on the disk. Then those values, in order for the processor to do anything with them, have to be read from memory and fed into processor, right? And some of these areas of memory want to be used more than once, more than twice, 3 times, who knows? And they might get cached. So, right, your RAM space here, 4 gigabytes, 32 gigabytes, it's gonna be a lot of space. Let's go. Hey, let's see what kind of space we have this semester. Come on, wake up. Interesting. Geolocation systems are funny sometimes. All right, first up here. So, right, our L3 cache is 32 megabytes. Right, memories are always getting bigger. The L1, L2, L3 cache, those get bigger. RAM gets bigger. Everything's get bigger over time. Right, 32 megabytes L3 cache. That's a fair amount. Let's see if we can find a cache mentioned elsewhere on this page. L1 and L2 are going to be quite a bit smaller. L1's probably going to be like 512 kilobytes. There we go, 384, right? So L1 cache, 384 kilobytes, and then L2 cache, 6 megabytes. Right, the data that's in these sets, pretty much we start from RAM, and then we feed our way up to our 32, and then 6, and then L1, right? So there's not a whole lot of space for L1 cache. And the difference between these caches, L1 cache is going to be the fastest cache. L2 will be faster than L3, but not as fast as L2 cache, and L3 cache not as fast. And RAM, of course, is take even longer time to get to. So, right, time it takes to get from the CPU to registers, right? Registers that's part of the CPU that's fast and it has access to. But if the data isn't here, then we have to go get it before we can load it. So we're going to check, is it an L1 cache? And if it is, right, send the data back. If it's not, we have to look further away. And then if it's there, send it back. If it's not here, right, keep going further away until we find it, or load it all the way up, going all the way to memory. And if we have, right, the term I said minutes ago, right, we can do virtual memory on disk. That's where if you have a disk that's a low amount of RAM, but you have all kinds of applications you want to load up, what you can do is you can use your hard drive as though we're RAM, and we can page a chunk out. So we'll take this chunk and then move it on disk, because that chunk hasn't been used for a while, or it isn't near other places we're using. All this space on the temporal locality and locality of reference of where and what's being used. Because if I haven't, say this was Excel or something like that, Excel's taking all this memory, but I haven't actually asked Excel, done anything with Excel for a period of time. So it'll, kick that out and then load in Zoom or something else in its place, because we can see that's being used a lot. And then Zoom's being used more, so we're going to see part of Zoom find its way up here in the cache. Not all of it's going to fit there because it's just not enough space, right? And then L2 cache, you're like, all right, we're using the zoo part of Zoom a lot. And the L1 cache is like, this Z section of Zoom, that's being hit even more so than other things. The hit count's high, the frequency's high, the timing is recent. So whenever we're in this part, just grab the pixels that changed and then throw those pixels across the stream. Find out which pixels just changed and then throw them back out of the screen. right? As opposed to, right, the chat window part's not changing much. So we can go ahead and unload the chat window bit of memory because not much is changing there. So we don't have to worry about it. Right, the annotate not being used very often. So we can shove that aside, or it's not used often enough to even make it into these higher level caches. So if you keep going forward, you'll probably get into a systems architecture class and they'll talk about CPUs and how all these fun things work, what the throughput is for things, all the fun stuff, and you'll figure out what bits of data should move along there, and it's all related to our locality of reference, right? So X and Y, we use them, right? I declared X, I set it to 10, then I declared Y, set to 20, declared total, set to 0, and then we got I working on here, we set to 0, and then I was used again a moment later, and then I is used again, along with total a moment later, and then I is used again, right? So I is a very hot object. Everyone keeps wanting to read and or write to that location of memory. So it getting up into the higher levels of cache are going to be very, very probable. Total is being used a fair amount, right? At 1/4, yeah, well, 1/3, because after the first time through, right, we're only looking at I 3 times per pass, right? Read it, increment it, read it, compare it against another value, and then we get in there. So total is being used 1/3. As often as I have X and Y, right? These are just getting stale. Every time the loop iterates, X and Y are just getting more stale, and Y and I and total are getting more trendy, I guess, is a way to put that. Right, so the hit count there, you're getting a lot more views on I and total than X and Y are, so it's going to become old news. If this was a function, right, these are all stacked variables, so our spatial locality will probably just grab it all anyways. Right, so spatial locality. Basic thing here is a resource. Your other resources that are being used or going to be used are more likely to be used in the near future than resources that are further away. Right, so going back to our image, and say we had all of our variables here. We had X, Y, I, and total in memory. When these get grabbed, right, the whole of it might get grabbed when it gets brought into L3 cache. When we're going to L2 cache, it's gonna be like X and Y, while they were close, they weren't close enough for my net because I'm using a smaller net when I'm grabbing data points to bring them up here. And then when we got all the way up here to our one cache, so yeah, we're not going to bother pulling total up here because it is near an area of memory that we're working on, but it's far enough away that we're not going to grab it. Right, so X and Y got promoted up here, even though they're not being used. So it's very possible that we'll drop them off after a period of time. But I in total, and I is being read and operated on quite often. So we'll make the changes here in our cache where it's closest to the core and just keep updating there and not bother with these slower areas of memory. So one of the drawbacks of cache is the stale nature of things. Data can get stale real fast. So these updates to I are happening in cache just at this level because there's no point in going through and updating I in all these other places. The whole reason for I to be up here is we can get the data and work on it quicker, right? So read operations, not a problem, because reads, as soon as I find it, I can send it back and I'm done. But when we're doing write operations, the value of I might be up to 10 over here. And say we did an update not that long ago, we had a 4 over there, and it's 2 over here, and it's 1 over here in memory. All right, so these state changes need to propagate back, but that takes time. And so we don't want to propagate back every single change we make to I. So every so often, cache will go and propagate the data back out to where its true state is being maintained here in local memory, and we'll get that at some point in time. And so that just means we have to make sure we're properly reading from that. Right? Application cache is something that will happen a lot. Most applications, right, are transient nature. You'll load the service up and it will pull data from an external source, not on the machine that's on. That external source is often a database, right? So when you're pulling data from the database, you're not necessarily the only service that is going to be working on that data. We may have a lot of services working on that data, and multiple people are writing the database. And if the application is operating off of its known state 3 seconds ago, that might no longer be an accurate picture of the puzzle. And using that in my work, we have new companies and stores being added to the system. The way the cache was designed, which is quite horribly, it just loads it all up in memory. So the 200, 2,000, 20,000, whatever companies that it found when the service started is what it sees in memory, and it's got cache there, and it's going to stay there for 24 memories. So this company exists, and we can run transactions for this company. And then tomorrow I'll check back later to see if there's any new companies that have floated around and come into being, and then we'll track that. So if we were to send a transaction at the service for the company that was newly created, service will be like, I don't know who you are, and I'm too lazy to go back to the database to find out if you've come along since I last checked, and it will hit a stale cache situation and improperly behave, right? And well-designed cache will either get immediately updated because someone externally said, hey, we added a new data point, which our system does have that detail, assuming that mechanism works, or it'll go back to the data source if it doesn't have it. But if, say, we have the reverse situation where company 1, 2, 3 is there, but they canceled their contract, and we want to go ahead and disable them from the system, right? In that particular situation, 1, 2, 3 shows up in cache, but that sub item within there saying that they're active in the system, that is out of date, right? So cache exists for performance reasons, but it's going to be a bane often, more like than not, in most developers' careers, because you're trying to figure out why isn't this working, why is this working, and the answer might be the cache was stale and it just did not have the right data. This is where good logs are super critical. You don't have good logs on what the machine was thinking about at the point in time, meaning what data was in its memory when it made a decision. It'd be very, very difficult to figure out why it made apparently the wrong decision doing whatever it was doing. Right, so with our spatial locality of reference, chunks of data get read, and same pattern would happen with disk. Right, when we're reading from disk, we're not going to read 1 byte at a time. Right, so reading memory, be it RAM, or disk, we tend to overread, reading more than just the number of bytes being requested, hoping that the next read hits that same block of bytes, and thus saving us the trip to the underlying storage. All right, so this particular pattern locality reference, to be going to sequential locality reference. Very often we read X bytes and then read the next X bytes after that location and rinse and repeat. Right, so that's, and we'll come to where computers work with von Neumann architecture. And see if I can remember how to spell his name. There we go. And image. Oh, that's right there in Wikipedia. And here it's Wikipedia again. An image sooner or later. Right, so the basic architecture is we will read an instruction, it's not the image I want. Let's see. Where's my fetch? Let's all right, let's see if we can find. There, I messed over it. All right, let's see. All right, here we go. All right. Again, don't worry about von Neumann architecture. It's simply an example of which where sequential spatial locality is used. You know the details of the architecture, but it's very cyclical in nature, right? So you start a cycle, end a cycle, and basically we're going to read an instruction, and then that gets sent along to the CPU to be executed. And then we come back around and we grab an instruction, feed it, grab an instruction, feed it. And a lot of the times that's where in which the code's going to do things. Now, when we have loops and function calls and branches and all the fun stuff, that causes it to skip. But if we expanded our code here a little bit. All right, add a few more here, more lines. All right, I'll just, let's see. It's all going to get complicated when it gets dropped down into assemblies. What can we do here? That's simple. Out branching. Yeah, total plus equals I. Let's see, we're going to do another I plus plus over here. And we're going to do a total plus plus. Terrible code. Right, so an instruction is read, moves something into the register, and all right, so this is a multi-part instruction. Again, when we're talking about instructions here, we're talking about machine level instructions, not mid-level or high-level programming languages. So that'd be one instruction, right? We have our test, we enter the body, right? So this goes to instruction, read the instruction, execute. Read the next instruction and execute, read the next instruction, execute, and then we hit the enter here, and it does a jump where our increment is, and then our test, and then either we jump back into the body or we jump past. So there's still some jumps going on here that causes things to break down, but one of the ways our locality references can be used here is we'll go ahead and read in a large chunk of instructions. On the basis of that, if I'm going, as soon as I read this instruction, and if nothing else is already cached in memory, we'll just read a whole chunk of code that's later in memory. Not too much when I go too overly ambitious, because the first thing might be go make this function call. And that function call is going to take us somewhere else into memory for where that code actually exists. Remember, all functions, like all a function is, and if I add, let's see out here. All right, our total so far, and I and L. Right, see, that's just a function call. Or the extraction operator is a function call, however you want to look at that. Which means we have to go somewhere else in code and pull that in. But since cout's probably going to be used often if it's a console-based application, right, that particular code will find its way closer to the CPU, right, our L1, L2, L3 cache, so that we can get to it quickly. Right, we don't want to go to a function, load it, do what it says, and then immediately unload it, go back to where we recall this and keep on doing things, right? Especially in loops, right? The same functions might often get called in the loops. So those functions, even though they're not spatially located, they're going to be temporally located because we hit that function not that long ago, and we want to keep it closer memory so that we don't have to spend time loading it up again. Arrays would be another place for spatial locality reference. You can use a lot, right? You hit the first element of the array, odds are the second element of the array is going to be hit next. It's reasonable certainty. Not guaranteed, right? We might be doing a binary search and that hits the middle element. So loading up a bunch of elements right near it. Might be in range, probably won't be in range because the way it jumps around. So that particular algorithm does not enjoy locality reference too much, the way things are going there. But let's see. What else? I swore I had another thought a minute ago, but it disappeared real quick. I think it was the arrays, but all right. Let's toss that up. Okay. Let's. I don't think I'm forgetting anything. Double check. What am I forgetting? Compaction, memory, friend, HTML. All right. Seems like I'm not forgetting anything at the moment. Would be the end of this section. All right, so test 5, hashing. Hashing is going to be a large chunk of test 5. Garbage collection is a good sized chunk, and then these last bits here. Let's any other questions about chaining before I close this tab? No, the final is not on the last section. The final is cumulative. It is everything. Refresh the tab. Okay. Let's see. Yeah, two submissions are theirs. It's one of yours. It is showing up. All right, next week, Thanksgiving week, we have test 4. And since it is Thanksgiving week, that is all that we're going to do on that test. Right? We are, let's see, we have 1, 2, 3. Yeah, 3 lectures should be more than enough to complete. Uh, what is going on here? Well, we messed all that up. All right, section 6, 6, 6. And go to the right semester. Right, we're gonna have data compression, custom codes. There's still a fair bit to go over here, so those should take most of 3 lectures. So we don't need next week to start digging into this. I'll get through these 3 first lecture and most of these next 5 in the second lecture, and then raid and Hamming code might be the last 2 for the last lecture. Right, and then we will have a review. Right, so that why is this showing on the wrong date? This is not a Tuesday class. Mm. Do. Get that right place. Make sure it's showing up in the right spot. Oh, yeah, Christmas is less than 6 weeks away. So 3 labs for this week's lab. Yeah, your graph list, sort link list, and the regular hash table and good reference points. All right. All right, so we have 1, 2, yes. So we have 3 lectures. All right, so the last lecture. Why the heck is this showing up on Tuesday? I don't know why lecture's showing up on Tuesday. Oh, I'm getting confused here. Okay, so we got a 27th, week later, 2, and then the 11th. And then for some reason this item's showing up here. That's interesting. That go away. Fix the way the class is looking here. All right. 1, 2, 3. Yep. So how are things coming along with program 4? And we briefly talked about this last week, so not surprised. Nothing's happened just yet. Right. You want to do the hashing, the chaining lab first. The chaining lab would then transform into program 4, right? Because we are using chaining as our collision resolution. But this time around, the key will be the name of the variable, and then all the other variable state would be the value that is associated with that key. So you should be able to use a fair amount of your lab as a primer for this program, and then it's writing the interpreter part. So let's talk about how that kind of thing would work. String line of code equals Rx equals 20 sort of thing. And change this a bit. Let's see, we have 5 lines of code here. Yeah. Trying to mix my languages here. All right, line of code. Right, more lines of code. Basic idea of the program is read a line. I use a get line of some sort type of thing. So that you're operating off of just a line. And then we've got our parts. Right, if it's a comment, do whatever comment's going to do. Relative parts sub 0 equals var. Whatever we need to do for when it's a var variable. Relative parts of 1 is equal to different keyword. One we're intended on it being. Otherwise, we're in an else case here, and then parts of 0 is a variable. Let's say we have line sub 1 is variable. Line sub 2 is now y equals 100. Sample y equals 100 type thing. Right, so the way our language works, the very first term, for example, right, ignoring white space, don't care about white space, but the very first word or token on a line of code is either a keyword or it is a variable. And that's basically all we need to. Where'd my tab? That's right. That's the basic idea of the interpreter. Okay, so there's a little bit of string manipulation. And it's just like a program when you read a line, and then is it an operand or an operator? Right. So now it's just is the first bit on the line a keyword or not a keyword? And then reading multiple lines. That is the rough exoskeleton for what the program is, except for you obviously don't hard code programs. Right, you will be creating your own custom org files. Oops. Let's go back to where we were there. We're there. If you're having a hard time reading from file, right? Reading from console is good enough. Okay. Don't remember how to do your if streams. Let's do a quick example on that. Steal it from stub. Where's my stub code? That's terrible. There we are. Right, there's no stream. Don't care about. That's a link. There is. Right, if stream. Right, give it a file name. Shouldn't have to bother giving it BIOS mode. It should be text as the default. Let's see in a second here. Let's give it. Create a file. Word.text. Oh, hello. 20. Index. Right. Keep the programs simple to start. When you're starting to build your program, right? Don't try to build the entire sample thing on one go. Right. Creator, word, text. Text should be the default. And then get line. Let me remember my get line syntax. Line file. Cookies, cookie. Get line into the file. Right. Right. Yeah, this kind of works just as well. Might as well take that. Right, that's what we call our file. We call that price. Stream. We need to find our line. Yeah, let's see what we got here. If stream. Why I didn't notice that wasn't in stream before. I am using the wrong one. Okay, hold on. What is open? All right. So used to creating these all in one go. File's not open. Go from the file. Let's see if we're running it. Oh, well, there's no file name. So we failed to open the file. If file has incomplete type and can't be defined. Okay. Oh, eh. Let's all the headers, I suppose. I'm doing that a lot in C++ class, or C class, forgetting my standard library headers. Failed to open the text. Okay. Not case sensitive, are you? Huh, we are case sensitive. How about that? I think we're using a Linux-based system over here. Different OSs would have different. Right, so opening from the file is in the requirements, but not opening from the file is perfectly good as well. As we can do a version, we just read from the console. Reload is totally not what I meant. So we do the same thing and just get line, get line. Right, and we can have the text as a source over here. Hello, or x equals 20, print x type thing. Just not quite sure. Let's see the line here. Get line. It's not equal empty string. Is that going to work? Let's see. Let's see. I'm spacing on get line. I need to specify the input stream. I didn't think I did. Apparently I did. Standard in. Okay. Give it to work. Do, 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 do. What's I forget? Does it have a void type? All right, I'll do a while one here. Mhm. All right, and if line is empty, then we'll just bail out. File start alias. Oh, CN. Sorry, I'm working in C mode here. Here be my problem. I think it's freaking out a little bit since my sample.
You don't do a video for it?
All right, so right, we keep getting the same old line over and over again. Let me check the return of get line. So this is gonna be the slightly bigger problem. Let's see. Run and interactive console. And let's see, line equals get line. No, doesn't like me doing that. All right, so this is one of the tricky parts when with reading from the file. It's seeing, man, I need to look at the chat more often because you're definitely finding my bugs faster than I am tonight. The end of the file is much easier to test for as opposed to the end of the input from the console. Might be able to force it this way. An empty string at the end after we're done using it. And we'll go back to run that version. Hello, empty string, go, and reading from text. Probably give us the same. All right, so we got to stop. Got to stop there. Nicely. So if you can get to stop nicely with using the input as text over here on online GDB, then it's fine not reading from a file. Okay, so my basic test setup, I'll have things like this for when you don't have a file, and or I will have file1.txt with the same content over here, because file processing is a pain in the butt in pretty much any language, especially since it's different for every language, right? When we do it in C, C++, in my primary language, C#, it's not the same. Okay, it's much easier over here if I was actually gonna do the file stuff, like system.io file, and I just say read all lines, and it just give me a nice big old string array for my board.txt. And super nice and easy. And now we're reading it all from the file. Right, so if you're getting hung up on the file IO is not the purpose of the assignment. So I don't want you to get hung up on that chaining hash table in the interpreter. That's where the purpose and scope of our program is. So either way will be fine from the grading perspective. And we talk after the test next week, we want to talk about program 4 again. If anyone's still around after the test, we can talk about it then. Otherwise, no lecture. After the test next week, we'll just talk about program 4, labs, or whatever code things we are needing to dig into. Right. Any questions about anything else for tonight? All right. I take the rest of our 30 minutes of break and 50 minutes of lab, and that will be